All right, so here we have linear and DC motors for 400. And as I've said before in like this module 3 of this class, it's worth your time to make sure that we understand all of the terms that are in our given statement before we begin solving, or at least the major ones, right? So here's a horsepower. This is, we'll get to that in a second, because we know that this is a P. Is it P out or P in? We'll discuss that in a second. First, let's grab these because these are easy. There's VDC. This one on the equation sheet is actually called RPM, and this is eta, which as a reminder is P out over P in. I'm writing that one because it's the only one on the equation sheet whenever I get a DC motor problem that isn't right here inside of DC motors. So if I have a DC motor problem, I can come right to this, and everything all the way down to that little circuit at the bottom, all of this is my DC motor equations. The only one that's not in that box is this efficiency equation right here, right? Eta equals P out over P in. Eta is efficiency. So that's the only one that isn't there. The other thing let's discuss is horsepower. So think about what horsepower is. If I'm thinking about a motor, it's my output power. And a tip is in this class, horsepower is always on the mechanical side. If we're dealing with electricity, we'll always put it in watts. They mean the same thing. One's just an English unit and one is a metric unit, but we always use electricity in watts. So if I see horsepower, it's mechanical. Note how on the generator, horsepower is also on the mechanical side, right? But even as far as like my DC motor, if I think about what a motor is doing, it's spinning something. You know, it's going to spin and pull my elevator up, or it's going to spin and make my electric lawnmower go. Whatever motor it is, it's spinning something, and so its output power is that is in horsepower. So we'll call that P out. Okay. So now the next part is we're being asked to find IA, that's current, find RA, that's resistance, find the machine constant, KV, and determine T load with no mechanical losses. And the one thing I'll say here is this would also be T out, right? Because that is my load, and it kind of shows it how we have a system that's drawn on the right, and the T load is on the output side, right? But the load is the out, and that's been consistent with all of what we've been doing the whole semester with loads. That's the output side. And just to be clear, the equation sheet calls it T out. So if I'm going to find I, the steps first is I'm going to always need to put, and it's always a safe bet, if I have a power in horsepower, then it's worth putting into watts, right? So 1 horsepower is 746 watts. And that's because everything that we're doing is all of this electrical stuff. 186.5 watts. I have P eta is P out over P in. So if I needed my P in, which is often when I'm given efficiency and a P out, it's going to be needed. But the reason I'm going to P in is because P in is where I find my current, right? It's an electric system. Motors are converting electrical energy into mechanical energy. So this electric side, I'm going to have to get to the input side in order to find an electric current. So P in is equal to P out divided by eta. P out 186.5, eta 0.96, and I get 194.3 watts. Note that my input is greater than my output. That should always make sense, right? If I look at especially this power flow diagram, this width from here to here is bigger than from here to here. It also makes sense that it couldn't be bigger because otherwise I'm adding in more things into the system. If I have one input, then I have these 3 things that are coming out of the system. These 2 in the form of losses, and the last one is my out, also called my load. So I can rearrange and solve for IA equals P in over V DC, 194.3 watts, divided by 28 volts, and I get 6.94 amps. There's part A. Part B is I'm finding the resistance. How do I find the resistance? Well, let's look at where is even the resistance showing up inside of our equation sheets. Okay, the only place where resistance shows up, I guess there's two. There's one at the bottom, but because nothing is being discussed about an induced voltage, right? Induced isn't being given here. So we haven't gotten there yet. So if there's no E induced, this one right here has P electric loss equals I squared R. And I realize now that this statement in this problem, this phrase up here, with no mechanical losses, that should be given in the problem statement. Because in order to find RA, we're going to use no mechanical losses. So at the bottom of the power flow diagram, it says P in equals P electric loss plus P mechanical losses plus P out. And it says no mechanical losses, so that one's 0. So my P in equals P electric loss plus P out. Oh, well now I have those other two parts. So I can solve for P electric loss, which is P in minus P out. P in was 194.3, P out 186.5, and what I'm left with is 7.77 watts. P electric loss is equal to I squared R. Well, I'm solving for R. So I have P electric loss divided by I squared, 7.77 watts divided by 6.94 squared. And that gives me 0.161 ohms, which is equal to 161 milliohms. There's part 2. Or part B. Part C, I'll do an orange, and it says find the machine constant, kV. Well, the machine constant, if we think about this power flow diagram, it's going to be right here in the middle. All of this is like my machine. I'm having input into my machine, and I have output. You'll take thermo, and you'll draw these arrows like this as your system, you know, with things coming in and out of a system, and that's really all we're doing here, is that I have this motor with electric input, and this is where it's transforming from electrical to mechanical energy with my machine. Machine constant is kV. So what parts do I know that I can solve for? Probably the easiest way, since I already know my power, and I know these right here. I know I don't know omega, but I do know RPM, right? So I can solve for omega and plug omega in. I know my power developed because in this case, this one was 0. If that one was 0, you can think of it as like, there's no arrow here. You know, like this, there's no mechanical loss. And so that's my new arrow. Everything that was developed is output power. There's a mechanical loss would be like friction. So another way to say that would be in a frictionless system, or assuming there's no friction, negligible friction losses. All right, so PD equals KV I omega. PD equals KV IA omega. So in order to do that, let's solve for omega real quick. Omega equals 2 pi RPM over 60. 2 pi RPM 3500 over 60. Omega looks like a W. Omega is 366.5 radians per second. We're going to solve for kV. So I have PD equals, or PD over IA omega. The power developed, in this case, because no mechanical losses, PD equals P out since P mech loss equals 0. There's even an equation that would straight up say that if we look right here under the power developed equals P mech loss plus P out. So if this is 0, P developed equals P out. So that's 186.5 divided by 6.94 and 366.5. And my machine constant comes out to 0.073. And unitless is probably acceptable. There are multiple ways to write it, this one, or if you just carried through what you wrote, volt over amps radians per second. If you wanted to be clear, that would be acceptable because that's what we plugged in to this formula. Okay, part D is asked to find that T out, right? D, T out. Well, the easiest one for this is P out equals T out omega. That's right here. Mechanical loss is 0. Well, actually, oh, never mind. It does call it T load. This whole time I've been saying T out, but T out is T load. So there we already just solved for omega. We have P out. So T load. I'll erase all those and call them T load since that's what we're finding. T load equals P out divided by omega. T load is equal to 186.5, 366.5, and that comes out to 0.509. And you should always put your torque into Newton meters. This case would be 509 millinewton meters. Another equation to solve for that is we could say that the T load, talking about torque balance, equals the T developed, since there's no T mech loss, T mechanical loss, which means we could also have done something like TD equals KVIA would be another way to solve that. Since there's no mechanical loss, this is 0, those equations would also be the same as T load for torque developed. Zoom this out to put it all on one page and can answer any questions about it.